Students, we are going to discuss applications of uniform circular motion. Applications of uniform circular motion. Our common observations that when we travel along the curved road, especially in ghatas, before starting the turn, we observe display boards on which it is written like this: speed limits 20 or 20 km per hour. So we have to take precaution that this speed limit is not exceeded. If we drive our vehicle with speed greater than 20 km per hour, then it may skid. So if we have to take precaution to go with the speed which is less than 20 km per hour. These speed limits can be obtained by using the theory of uniform circular motion and considering various forces. So our first application is related to speed limit. Vehicle along horizontal curved road. Horizontal curved road. So here, if there is a car traveling along the circular road, for the situation we have to obtain the value or expression for speed or velocity. Here we consider the center of circular road somewhere here and the radial part like this road like this. Actually, section of road we are considering, and avoid the showing of curve. We show only here a vehicle which is a car, suppose, and wheels of car are shown like this. Center of gravity of car is somewhere here. Weight of car is shown vertically downward, and this road surface exerts normal reaction on the car is shown vertically upward and denoted by L. Here, when the road surface is in contact with this tire, there exists a force of static friction. Here, force of static friction comes into play when there is contact between road surface and tire surface. This is the force due to static friction or force of static friction directed towards the center and along the radius. So it provides necessary centripetal force. It can be written as Fs is equal to mv square upon r, where m is mass of vehicle, v is speed with which the vehicle is traveling, r is radius. Radius can be shown from center to the outer edge of the vehicle or road, and force due to normal reaction, N is balanced by the weight. Now from these two expressions we can write Fs divided by N is equal to V square upon Rg. Means simply dividing, suppose this is first equation, this one is second, dividing first equation by second equation we get such relation. Adjustment gives us Fs is equal to V square upon Rg multiplied by N. For the given system, N is constant, R is constant, we can write Fs is directly proportional to V square. Means when V is 0, Fs is 0. When V is maximum, Fs is also taking its maximum value. Fs can take its limiting value, and according to law of static friction, Fs maximum is equal to mu s into n, where mu s is called as coefficient of static friction. This value of mu s depends on the road surface and tire surface. Now from this relation, substitution gives us the equation for maximum speed limit. Here Fs can be substituted as mv max square upon r. It is equal to mu s into mg, because we have shown here in the diagram n is balanced by mg. So we get mv max v max square is equal to mu s into rg, and v max can be written as under root mu s into rg. So this is the maximum speed limit with which the vehicle can be driven along the curved road. So by knowing the values of mu s and r, we can calculate the value for speed limit for that particular road. Here, if the speed is less than V max, means if the car is traveling with a speed which is lower than the maximum speed limit, then the car will be safe. If the speed limit is exceeded, then the car will not be safe. The car may skid along the tangent. So this is about the maximum speed limit for a vehicle along horizontal curved road. Now the second application is, again we have to determine the speed limit for wheel of death. Wheel of death. Here you have seen in jatras, in circles, that wheel of death, there is motorcyclist taking turn in the cylinder or stunt riding over the motorcycle and taking fast horizontal fast turns along the horizontal path, circular path. That is the wheel of death and can be shown here by the cylinder. Like this. Here the cylinder in which motorcycle and cyclist undertake horizontal circles. Here there is a point P. Interior to the wall, motorcyclist and motorcycle is there, and the weight of that system is vertically downward, shown by mg. Here, when motorcycle is in contact with the wall, there is force of static friction, but it acts vertically upward in this case. Here, this force avoids the falling of motorcycle in the downward direction, and there is one more force towards the center of the circular path, horizontal circular path. Here, that force is the normal reaction. It is the reaction exerted by the wall on the motorcycle and motorcyclist, that system. So, as this normal reaction in this diagram is directed towards the center along the radius of circular path, here we show circular path like this, then this N is providing here the necessary centripetal force. So we can write the relations like this. Here, for wall of death, Fs is equal to mg. This is our first equation. And N is equal to mv square upon r. So this is the second relation. Now, for this well of death or cylinder, we take Fs, which is less than or equal to mu s into n. Not the limiting value or not the maximum value, but we take here force of static friction less than the normal reaction. Then substitution gives us Fs is substituted as mg is less than or equal to mu s into m into v square upon r. Adjustments gives us rg upon mu s equal to v less than or equal to, not equal to here, less than or equal to v square. We can write v square is greater than or equal to rg upon mu. But here, instead of greater than or equality, we take it as v square is equal to rg upon mu. And this is for the lower value of velocity, therefore it is denoted by v mean. V mean square is equal to rg upon mu. So greater than inequalities avoided here for the minimum speed. So v mean or lower value of velocity is equal to under root rg upon mu, or here we have to denote it by mu s. So this is the minimum value of velocity with which motorcycle has to undertake the turns, horizontal turns here or horizontal circle here. He has to complete the horizontal circle by taking this minimum value. So if V is greater than V minimum, then the system is safe or the stunt is safe. Stunt we call here, stunt is safe. But if V is less than V minimum. If very small velocity is taken by the motorcyclist, then it will not safe. The vehicle may fall here. Here there may be fall of the motorcycle, or it may fall inside the cylinder. So here we have to use minimum speed limit with which the motorcyclist can undertake or complete the horizontal circles. So these are two applications of uniform circular motion. In the next lecture also we continue applications of uniform circular motion. Now, based on these 2 points, you have to write short answer questions related to the derivations of the velocities. In the last case, we have to derive maximum speed limit for the vehicle along horizontal road, and for this application you have to derive minimum speed limit. Also, the next problem or question for homework is that you have to solve the numericals based on these speed limits. So we stop here. Thank you.